Okay, so in that first example, G13, we were able to use sine and cos, but we haven't hit tan yet. So let's consider now how we would differentiate tan using the knowledge that we have. Well, after completing the trig work in A2, you will know that we can write tan as sine over cos. And using the differentiation work that we've covered, we recognise that what we've got there is a quotient, where the top of the quotient is u, bottom of the quotient is v. So using the quotient rule, we let u equal sine x, v equal cos x. We differentiate sine, we get cos, and when we differentiate cos, we get minus sine. Quotient rule, just to remind ourselves, is v du dx minus u dv dx all over v squared. So v is cos x times du dx, which is cos x, minus u, which is sine x, times dv dx, which is minus sine x, all over cos x all squared. So cos times cos is cos squared x, plus, because we've got a minus times a minus, sine squared x all over cos squared x. Now from your trig work, you should spot one of the first trig identities you meet, which is cos squared plus sine squared is 1. So that becomes 1 over cos squared x. From your trig work, you know that 1 over cos is the same as sec. So you end up with sec squared x. So when you differentiate tan, you get sec squared. Now, you were given a limited number of standard derivatives in the WJAC formula book, which I've snipped onto the second page of the notes. So tan is one that you are given. It's helpful if you recognise or you can remember that relationship, because quite often, in particular when you're integrating and working backwards, it's useful to be able to spot these and remember what the derivatives are. But you can see there sine and cos aren't provided, so you've got to learn those. So the tan one you are given, but it's useful to know where it comes from. Okay, so that's tan. Next one, Kosak. Well, you should know that you can write Kosak as 1 over sine. And using indices, I can write that as sine x to the power of minus 1. Now this is really important, going back to what I said in the previous example where you've got sine cubed or whatever. In maths we often write sine to the minus 1 of x being the arc sine, the opposite of sining, and even on your calculator you will see that sine to the power of minus 1. That's not what I mean by sine x to the power of minus 1. So you need to be mindful of that. Right, so I got a chain rule. I've got the sine of x embedded in my reciprocal to the power of -1 function. So when I differentiate that, I get -1 finger to the power of -2. So -1 sine x to the power of -2, and I'm multiplying that by the differential of what I'd covered up. So when I differentiate sine, I get cos. So that I can write as minus cos x over sine squared x, taking the negative power back down, which I can write as minus cos x over sine x times 1 over sine x. Means the same thing. Yeah, minus cos on top, and I've split that sine up. And the reason that I've done that is because I know that cos over sine is cot, and 1 over sine is Kosak. So when I differentiate Kosak, I get minus cot Kosak. Which is a bit of a mouthful. So it's probably good news that that one is one that you are given. Kosak is minus Kosak cot, or cot Kosak as I've written, it doesn't matter. So that's Kosak. Next we've got sec, and we'll go about doing that in exactly the same way as we've just done there. So C y equals sec x. Well, I know I can write that as 1 over cos, which I can write in index form as cos x to the power of -1. It's a chain rule. Cover up your finger, -1 finger to the -2. Multiplied by what I covered up, differentiate. So differential of cos is minus sine x. So this time the minus times the minus goes. So I'm going to have sine x on top and cos squared x underneath. So I can write that as sine x over cos x multiplied by 1 over cos x. Sine over cos is tan. 1 over cos is sec. So when I differentiate sec, I get sec tan, or tan sec. And that's another result that we are given there. So sec tan, or tan sec. And then D is cot. Well, I know the cot. Two ways of doing this. Now that we know what the differential of tan is, because you could start that by doing, well, cot is cos over sine, use the quotient rule. But because we know what tan is, I can write this. Sorry, no I can't. I can write that as 1 over tan. I can write that as a reciprocal. And now, using the chain rule, differentiate my finger, -1 finger to the -2. Multiplied by differential of your finger, We differentiate tan, we've already shown we get sec squared. So let's see how we can tidy this up. I'm going to have minus sec squared x over tan squared x. Well, that the sec squared is going to be 1 over cos squared, and tan, that is going to become, so tan is sine over cos, we could write it as cot, which would be cos squared x over sine squared x. So this bit here is the sec, that bit there is the 1 over tan. And what happens is the cos squareds cancel, meaning you're left with minus 1 over sine squared. 1 over sine is cosec, so that leaves you minus cosec squared x. So therefore, when you differentiate cot, you get minus cosec squared. And that's another one that you're given, so you can just write straight down. And with all of these trig functions that we're differentiating, and when you come to integrating, they're all valid for angles measured in radians. So if you were given something with an angle that you had to work at a gradient of, and the angle is given in degrees, you would need to change that angle in degrees into radians before substituting into the function. That's really important to remember. So that means now you're equipped to differentiate, in addition to exponential functions, natural log functions, products and quotients, and embedded functions. You can now tackle expressions which have got a whole different range of trig functions in as well. With any questions on differentiation and integrating, the more of them you can practice, the better, because they've all got slightly different little twists and tails in them.